we know that all of you have done a course in mechanics. So, we will be first we will look at linear motion, modeling some human movements as linear motion, then we will look at modeling it as angular motion, and then we will look at generating some equations of motion as we so that we can look at the time progression of different types of motion. So, if you look at any object in space can be thought of collection of a system of particles as a system of particles, right. It can be idealized. So, essentially we take them as small mass elements that can be idealized as a system of particles. Now, for each particle in the system, particle I in the system. So, if you take a system of n particles, for each particle I in the system, Newton's laws of motion will hold, right. Newton's laws of motion will hold. So, I can say that F I plus sigma over I equal to 1 to n small f I j equal to m I a I. Okay. When I put a bar, I am denoting them as vectors, where F I is the net force exerted on particle I by particles external to the system. So, these could be contact forces, gravitational forces, etc., but these are forces that are external to the system. These are the forces that is the net force exerted on particle I because of external reasons. And my F I j is the force exerted by particle j on particle I. So, a particle cannot exert a force on itself. So, F I equal to 0. Now, if I sum this over all the particles in the system, okay, I get sigma F I plus sigma sigma F I j equals sigma m I a I. Okay, for the system I get this. Sigma F I here is all the external forces. On the system, yes, external forces on the system. So, these could be contact forces, gravitational forces, and then this is the sum of all the internal forces in the system. What is this equal to? This is equal to 0. Why? Because of Newton's third law, because for any Fij you have a minus Fji, okay. Because of Newton's third law you have therefore, this shows that the internal forces do not contribute to the acceleration of the system. Okay. Therefore, your equation reduces to sigma Fi equal to sigma Mi Ai. Now, the linear momentum L of a system of particles is defined as L equal to sigma Mi Vi. Okay. Sum of the products of the mass times mass and velocity. So, if I differentiate this, dl by dt is sigma Mi dVi by dt, which is nothing but sigma, because m does not change with time. So, I have this is equal to sigma Mi Ai. And therefore, we have sigma f of I here is equal to essentially dl by dt. So, if a body is at rest or moving with a constant velocity, then its momentum does not change, momentum is conserved, right, and that is the case where you have sigma Fi equal to 0. That is the statics situation that we looked at. Okay. So, sigma Fi equal to 0 is your what we did for the last several classes, where we said if the body is at rest, we mainly looked at the case of bodies being at rest and we summed all the forces to be 0. Now, the center of mass of a system is defined by mi into RC equal to sigma mi Ri. So, if I have a coordinate system, okay, and I have various particles, okay, mi, mj, etc. The center of mass of the system is where the mass would be concentrated. The effect is the same as concentrating the mass at that location, and the location of that is defined by RC. Okay. So, this is sigma of mi. So, this is the definition of the center of mass. So, sigma mi is the total mass in the system RC is the, so center of mass is also usually denoted as COM, is the position vector of the center of mass. Mi is the mass of the ith particle or element, and Ri is the position vector of the ith particle. The velocity of the center of mass Vc, velocity of any point is just the rate of change of its position vector, right. So, it is drc by dt, and the acceleration is the rate of change of its velocity. So, if RC from here is sigma mi Ri by sigma mi, then Vc equal to drc by dt is nothing but sigma mi Vi by, if I differentiate both sides, sigma m. Okay. And similarly, the acceleration is sigma mi ai by sigma mi. Therefore, I got sigma Fi equal to sigma mi ai. Okay. So, from here I can write that as this is equal to sigma of mi times the acceleration of the center of mass. Therefore, the net external force acting on a system of particles is equal to the mass of the system times the acceleration of its center of mass. Say I represent the human body as two rods. So, for instance, I say this is one particle connected by a joint. So, remember in these kind of diagrams an open circle typically represents a joint, whereas a solid one like this usually represents the mass concentrated at that point. Let us say I have rod of mass m, two rods connected by a joint. Let us say each one is of length L. Each of length L and mass m. Okay. Now, let us say I choose a coordinate system xy coordinate system and I want to find the center of mass. Let us say this angle is theta. What is the center of mass of this system? So, I can say that m plus m into the x coordinate of the center of mass, okay, is essentially equal to sigma m I r I, okay, the x coordinate, right. So, let us say for the first mass my x coordinate is 0, yeah. For the second mass my x coordinate is, I have, this is L, so this is L by 2 m L by 2 into sin theta, okay, this here sin theta. So, x c is essentially equal to L by 2 sin theta. Sorry, L by 4, no, by 4 sin theta. Similarly, to find the y coordinate, I have m plus m, y coordinate is, for this one, for this particle, the y coordinate is L by 2. For this, the y coordinate is L plus L by 2 cos theta. So, my y coordinate is three L by plus L by cos theta. So, you can see that the center of mass of this system is going to change as theta changes. So, if you look at the human body, you can talk about a center of mass when you are in a particular posture. You move your limbs, or when you move from that particular position, your center of mass is going to change. So, you cannot say that there is one center of mass for the body. Okay. So, here you can see, if I lean forward, I lean more, my center of mass is going to change. Okay, if I think of this as this representing my lower body and that representing my upper body, the simplest case where I am modeling it as two particles. Okay. So, I can see that my center of mass will change as the posture changes. Typically, for a person who is standing in the normal standing position, for adults, I think for the center of mass from the ground, it is located at about 55% of the height. For females, so from YC, and about 57% of the body height for males. Okay, this is the typical, this is for the normal standing position. You remember, so it is located at the level of the second sacral vertebra. Okay. And you remember when we talked about the anatomical planes, we talk about the principal planes bisecting the center of mass. So, the origin would be at the center of mass, the point where the three planes intersect, the sagittal, the frontal and the transverse plane. We talk about the principal planes bisect the center of mass, and of course, any planes that are parallel to them are also called, so a plane parallel to the sagittal plane is also a sagittal plane, but the principal sagittal plane is the one that bisects the center of mass into left and right parts.